Today's little exercise is to try and draw one of the P&IDs. And let's just start off here. I said I would look at this P&ID here, which is the methanol column and the methanol product cooler. And we're free to change things around a little bit if we want to. And one of the first steps to do is to sit down and create a little 8.5 by 11 version of what you want to draw, just to kind of lay it out. And I'll kind of do this on the board, but I've already I sat down for 10 minutes and just threw something together. And it occurred to me that I wanted to bring this valve inside the envelope here, so I've done that, and you'll see that. Okay. So the first thing you want to do is just get a sense of the overall layout in the drawing. So start with a real quick version of it. Let's just draw a little tiny version up here and just get a sense of the layout. So it makes sense that we're going to go from, we want to go from left to right. We're going to have our distillation column either in the center, or maybe you want to put it off to the right, but I felt like I wanted to put it a little bit off center of a little left of the center, because I'm going to bring my flows that come off the tower and the equipment down into kind of this region here. But because I know I'm going to start to block myself out in here, I decided to put my reboiler in here. Oh, you know what we need? Does anybody have their equipment list with some of their equipment details? Can somebody pop it open and you can feed me information about your equipment? You guys good for that? Okay, so I think I'm going to put my reboiler kind of here. I know I've got to get a product cooler in, and I think most people were coming up with small product cooler sizes, so I think you're probably using double pipe heat exchangers. So I'm going to put a small double pipe heat exchanger roughly about here. I'm going to need some reflux pumps, and they need to kind of sit on the ground. And so I'm going to put those here and here. And I need to get my reflux drum in on top of that, roughly like that. And on top of that, I need to put a condenser like that. And there's a good chance that I'm going to need some bottoms pumps to send this material off to the waste treatment. So I'm going to show that. I'm going to show those there roughly. And so it's going to look kind of like this. There, off to there, like that. And my reflux pumps, one's going to go off to there. And my reflux is going to have to go up into here. Okay, so that just kind of gives me a sense of how I want to lay the drawing out, and I can just before I spend a lot of time drawing stuff and then erasing it, and then these are going to have to go off the page here, that's going to go off the page there. We're going to have a vent that goes off there. We've got to get the utilities on there, so I'm leaving space to put utilities. I'll put utilities kind of here and here. I'm going to need a whole section of utilities kind of here. I'm going to need some space for some utilities here and here. And I think also some people were putting heat exchange. I think we need to put a heat exchanger in on the bottoms. So this is going to get to be a crowded P&ID, that's for sure. So we can already tell that maybe we might want to start to think about splitting this up. So this would be the bottoms cooler here. So I feel like I'm going to get crowded down here. I could start to flip things over to the other side, but then I'm going to lose my left to right. So probably what I want to do is get the tower a little bit more off to the left when I draw the real version of this. Yeah, you could put the valve in if you want. Yeah, you can put the valve in. So I'm just trying to get a sense of the layout. of it. Does that look aesthetically not too bad? I'm trying to get the stuff roughly in elevation. I don't want to get the condenser too far up on the tower, otherwise it starts to look like more like a process flow diagram than a P&ID. A good rule of thumb for a really detailed set of P&IDs, a finished set of P&IDs, is not unusual to have maybe 1 or 2 pieces of equipment per sheet. So we're going to end up crowding our P&IDs a little bit more because we're not going to have the same level of detail of instrumentation and piping on it. So we can get more equipment on ours, but a good set of P&IDs won't have very much equipment on it because you just can't fit it all in. And there's lots of controls around the motors as well. So you want to leave yourself some space in here for motor controls. And we're going to have some space for the utility controls on here. So that's something else I got to think about in terms of space. Okay, so I'm gonna really try and push the tower off to the left here. Okay, so I've got a rough layout here. I've kind of thought through the gravity that I'm going to work with here already. I haven't really thought through the two-phase flow situations yet. There isn't too much two-phase flow here, except right here, you guys. There's some two-phase flow in that line there. And I've got the simulation so we can pop up some of these numbers and look at it as well. I've kind of thought through, I've kind of shown the pumps down in the bottom, and I may have to stagger them a little bit, but it'd be nice if I could have them right along the bottom. That would be an ideal situation. If I do that, I may end up with some lines crossing that's going to make it a little bit less clear, but that would be an ideal situation. And I haven't really done it. This is my first 8.5 by 11. I might actually sit down with another 8.5 by 11 and actually draw the instrumentation on it as well. It will get really messy, and that's kind of what I did just really quickly this morning. It's hard to see that, but you can see I just kind of blew the instrumentation on there real quick, just kind of get thinking about it. And I was thinking about it last night a little bit as well. Okay, so I think I'm in a position where I can probably start to draw it. And the version that I'm going to draw, well, I guess one thing we should do is we should put a title block on. And just so that I can keep things nice and large, I'm going to draw the title block over here. And this is going to be the methanol column P&ID. And you should put your name and your date and the sheet number or the drawing number. What drawing number is this going to be? We do need to give it a name, a number. Okay, so I think we called that one number 2. Is that right? Is that right? Yeah. Okay, so that's going to be number 1. So this is basically going to be number 3. So we're going to call this sheet 3. And we can reference, since we know what the sheet numbers are, 1, 2, 3, 4, 5, 6 maybe. We can put the sheet number references on the side of the drawing as we're going along here. Okay, am I ready? I think so. Any questions so far? Okay. So let's get my reboiler in here. What kind of reboiler did you guys use? Dave? Anybody? Anybody got their reboiler? You guys used a kettle reboiler? Okay, we could do a kettle reboiler. Okay. Okay, so I'm just thinking about the kettle reboiler. I want to bring the steam in from the left. So I'm going to flip the kettle reboiler around so it's kind of shown this way. Is that because of the area, or you just decided to use a kettle reboiler? If you wanted to increase the capacity? you could run bigger flows. Okay. Okay. I would have gravitated towards a thermosiphon first try. But so the P&ID will look a little bit different for a thermosiphon versus a kettle reboiler, but it's not a big deal. Okay, let me just think about this one. I might end up having to put the reboiler over here just because I'm going to have a lot of flows going off to the right. Nah, let's do it over here. Okay, here we go. So I want to draw the head of the kettle reboiler. There's the outline there. I'm going to draw the tube. I'm going to draw the tube sheet here. There's the tubes in the kettle reboiler. I'm going to put a baffle so I have an overflow on the kettle reboiler. So the liquid level is going to sit kind of there. I'm going to show my steam coming in here with a nozzle and my steam coming out. I need a vapor. Actually, one of the advantages of the kettle reboiler is it's an ideal stage of separation, which is a good thing. And I'm going to need an inlet here. Put it right in the middle so that I have good flow. It's a low viscosity fluid, so kettle reboiler is a good call there. We're not temperature sensitive, so that should be okay as well. Okay. I want to get a little bit of space in here before I put my tower in. Okay, so I'm going to put my tower in right around here. I'm going to do that. It's not a very straight line, is it? I'm going to make it nice and big. Hopefully my markers aren't going to run out. That would be bad. Okay, like that. Well, it's going to make the level control complicated. It's going to make the level control a little bit unusual for you guys, but that's okay. Okay, so there's my tower. And I need to get my bottoms pumps and a cooler in here probably, my reflux pumps, that, and the reflux drum, and the condenser about there. Okay, so let's put those in. There's one pump. And I need to leave myself lots of space. Let's go up a little bit. Ooh, that's bad. Okay. I'm gonna go up a little bit here. Okay, there's my pump. Here's another pump. Like that. So I've left myself some room for controls here. Let's put the bottoms cooler in right now. What kind of bottoms cooler did you guys build? Shell and tube, yeah. You know what TEMA class it was? An AE what? How about an AEU? Okay. There we go. A nice little AEU. No, that's a B. There we go. Does that look about right? Okay, so that should give us our bottoms. Now let's think about the overheads here. We're going to need another cooler, and we can put the cooler probably here. The pumps probably there. I think that should kind of work for me. you know what your overhead cooler was? Double pipe probably, right? Because it was pretty small, I think people were telling me. Okay, so I'm just going to draw it really as a straight line like this with a line through it. Sometimes they'll flip back on themselves, so people will draw them kind of as almost like a U shape. Flange on like that. Okay, so there's our overhead cooler. And how's my sound? I think we're okay? Yeah. Okay, so let's put the bottom, the reflux pumps in. Let's just offset them maybe. That might help me with a little bit of space here. Okay, there's one there. There's another one there. Let's draw the nozzles off the right. Oh, okay, now actually one of the things that you have to do here is you have to decide whether you're going to use one pump or two pumps here. So let's just fire up the model. And let's go into the simulation just quickly here. Performance, column profiles. Okay, so here's the deal, guys. I've got 18, almost 19,000 pounds per hour of liquid going back in as reflux, and about the same, it looks like, as the draw. So I don't have any one flow that's really dominating. I haven't done the hydraulics calculations, but this is a fairly tall tower, so this probably will have the greater differential pressure than this one that's going to go out to the storage tank. So, but I don't think it's going to be that different. Like I'm not going to two processes where one process is dramatically different in terms of pressure that I have to get it to. So I think I'm okay just to put a single set of pumps for those two destinations in. That's my guess at this point in time, not having done the pump calculations that we'll get to later on. So I'm gonna draw the P&ID with the assumption that I can do this with a single pump. We're putting two pumps in because of our spares policy, though. Does that make sense to you guys? Okay. So the next thing I need to do is put my reflux pump tank in. And you know what? I want to draw it a little bit bigger because we want to draw lots of controls around it. Okay, there's my reflux tank. There's my normal liquid level. And I might as well draw that up right now. I need to get all the little details around the pumps on there. But before I do that, okay, how about the condenser? What did you guys use for your condensers? Condenser? One condenser or two? One? Okay. What was the TEMA? AU. Okay. AU it is. Okay, I'm going to draw the cooling water coming in. Here's a choice. I could bring the cooling water in from the right and break the sort of tradition of going from left to right, or I can bring it in from the left and hold it that way. But it might get a little complicated because I'm going to have to draw the cooling water in coming across the tower or coming in from the top and dropping down through there. So I'm just sort of thinking about that right now, and I think I'm going to stick with it left to right for now. And since it's an AEU, tube sheet. And I know that reflux tank is actually a separator as well. At least I think you guys sized it as a separator. So I'm going to draw that, that line for the separator coming off right now. The only thing is, I don't know whether we've got it on here or not. Oh, wait a minute, I did want that. You're gonna help me? Yeah, okay, so there's my draw there in terms of vapor coming off there. And it is about 228 kilograms an hour versus what's coming into the condenser, which is several orders of magnitude larger. And most of the composition of that stuff is hydrogen, which is, well, not most of it, but a big chunk of it is hydrogen. So it's really quite light relative to the methanol in terms of its density. And I'm just thinking, I might be a little bit worried about this because I'm going to be coming into the condenser with very high velocity gas. It's going to be condensing through the condenser, and because we condense nearly, I don't know what it is, 99.9% of it. You do the math, I guess. But a very high percentage of it. So down at this end of the heat exchanger, the velocities are going to be really, really low, exceptionally low. Like the gas is just going to be drifting along. And what I'm thinking is the hydrogen is actually going to drift right up to the top of the condenser here, and it won't actually come down into the reflux tank. What will happen is it'll just sit at the top of the condenser, and it'll blanket the condenser, and it'll stop me from actually really running the condenser very efficiently. So I'm pretty certain that I need a vent on that condenser, on the high point. And it wouldn't surprise me if we could probably vent all of the vent off the condenser instead of off the reflux drum. Anybody think about that when they were sizing the reflux drums? You guys are smiling. You were thinking about it, right?
And then we were like, oh, it's a vapor liquid, it's separator, so we thought that the vapor had to go through to the reflux drum.
Right.
So that's why I said that.
That's, well,
But yeah.
At least you thought about it.
Yeah.
At least you thought about it. That's good. That's really good. So what we might want to do is we might want to provide vents in both places, just to be on the safe side. So I'm going to show that on there. Okay, so I've got my kind of my stack up, and I'm going to bring my vapor in here. Oh man, these pens are going to drive me crazy, aren't they? I didn't bring another pen down with me. Okay. And I got to come up here, but I want to leave some room at the very top in case I want to bring my cooling water in. Okay, so that's the first lie that a P&ID tells, because that line would actually really hug the column coming down. So, and just because of my layout, the P&ID does not really show the real process all that well. But we all kind of know what it should look like. Now, we could probably start to bring some of the feeds in. That's basically most of our equipment. You said that was a U-tube. We made a little executive decision there. Did I miss any equipment, you guys? No, I think we got it all. So now let's pipe it. We're coming in on stage 13, and what tray number is that then? Anybody know what tray number that is? 13 out of 25. What's your total number of trays in your column?
57.
57?
And
Okay.
our feed is coming in at 37.
57, and our feed's at 37. Okay. Everybody agree with that one? Okay, so we're gonna have to draw, we need lots of space to draw all the trays. And let's bring our feed in here. Because it comes in at the bottom, it's actually not a bad idea to kind of show it down here. I'm going to give myself a little bit of space here just so I don't get blocked in. And that valve that's the level control valve for the upstream, the LG separator, I'm going to put that valve here. Now what I've done by doing that, I'm thinking about this, is I have now put a two-phase flow mixture into this line. This is operating on the upstream side of this valve at 75 bar. This on the downstream side of that valve is operating at 2 bar plus my static head and all the pressure drops and things like that you guys did during the simulation rationalization. So I'm just going to guess that it's about 4 bar, just a approximation. Okay, so I know I'm going to have some two-phase flow there. I might go to the model and just check what I've got. So this is the that's the stream that's downstream of that valve. It's a little bit lower pressure probably, so I would have more two-phase flow. What it's telling me is that I only have about 250 pounds per hour of vapor in a stream that's 22,000. So it's a fairly low mass percentage, but in terms of two-phase flow, it's not mass percentage that counts, it's the volumetric percentage. And so what it's really telling me is I've got 29 actual cubic feet per minute, which is a pretty low volume. And the liquid flow rate is not very clear. It's not in the same units, so it's 56 gallons per minute. I need to convert that into, okay, well, let's do it in meters cubed per second. So 3.5 e to the minus 3 meters cubed per second versus 49 actual cubic meters per hour. Oh man, I need somebody give me the relative percentages of those. I'm guessing that I don't have a lot of gas flow in that line relative to the total volumetric flow rate. So I think I'm okay to put that valve down there and just let it come into the tower and separate in the tower itself. So I'll bring it in either on a tray or at the top of a downcomer, so that when it comes in, the vapor can go up and the liquid can go into the tower itself. That's what I think I can do, but maybe you guys can just confirm that. And that's coming from sheet 1. Okay, so we need to label that. Should we switch colors? Let's try that. From the LG separator. Sheet 1. Okay, so that's good, except the only thing is that LG separator's got a level control, so I need to send a signal to that valve. Yeah? Jen, that'd be great. Thanks. Thought I had everything planned. Thanks, sir. Okay, so it's a it's a hardwired signal. Oh yeah, this is great, perfect. And so it's a series of dashed lines into the valve. Since if I have a failure in that valve, I want to isolate. I don't want to have 6,000 or 60 bar or 75 bar all blow into my distillation column all at the same time. I'm making that a fail-close valve. No question about it. Okay. So that's the feed system. Let's do the bottoms of the tower. Like that. Liquid into the reboiler. Vapor back up into the reblower there. I think I won't put any valves in there, so that if I have to do maintenance or anything like that on the tower, then essentially I'm going to have to shut the tower down and de-inventory it all before we can get into it. That may or may not be a good idea. Might want to rethink that one over the next couple of days. Okay, we need to get some steam in there. Steam should be coming into the top of the heat exchanger. Does anybody know what pressure steam we need to use? Simulation rationalization / anybody got the steam?
Medium pressure.
Medium pressure steam? Okay. In like this. I want to put a manual isolation valve so I can isolate the steam supply. I'm going to do I'm going to measure the flow, and I'm going to put a flow control valve in here. I'm going to fail at close because the last thing I want is for the steam to go full on the reboiler, and so I'm making that a fail close valve. Like that. My steam is going to condense in the heat exchanger, and so I'm going to come out with a steam trap to stop live steam from blowing into the condensate system. Here I'm going to break my rule to condensate return system. So I have my steam trap in there. I'll put a little bypass around the steam trap. Whoops, valve, not steam trap. Okay. And there's no guarantee that you've actually got dry steam coming through this system. So a lot of people will actually put another steam trap in upstream of the flow element. This isn't something that I would expect you guys to automatically know, but a lot of people will do something like that. Just so that you've got relatively dry steam going into the heat exchanger. Okay, so now we have a flow element. Probably just use an orifice plate because I'm not that worried about accuracy. And I need a flow indicating transmitter here. And I need a flow indicating controller. Connect them all up with a wire. Okay, so now I have flow control on my steam. I'm going to have to decide what actually is going to control that flow. Let's look at the bottoms. Yes?
Why do you need a bypass on the second steam trap?
You generally put a bypass on the steam trap so the steam traps are notoriously unreliable. So if they want to do maintenance or check the steam trap, replace the steam trap, then the person will come in, they'll isolate the steam trap
The
and
second one on the left. Because if you'll just start putting like your steam right out.
yeah, it will, but they'll just throttle it in the time that it takes them to.
So why can't you close it?
Why can't you just close it? You probably could. You probably could, but generally they have almost like a standard steam trap arrangement, and every time they put a steam trap in, they just put the same arrangement in. You mean why not just let the water go through the heat exchanger?
Yeah.
For a short while, you probably could. I think for a short while, but it's probably just bad practice to do it. So you're better off not to have two-phase high velocity.
Still have water going through anyway. You'll just have.
No, you won't have water until you get to here.
No, if the steam's wet.
If the steam's wet,
Because that's the point of it, right? To get rid of.
to get rid of the water.
But if it's just going through a valve, you're just splitting the steam off into two. You're not getting rid of the water.
Well, the way the piping would actually have to be done is this. You usually would have to come down from like the pipe bridge, and then they'll have an elbow or a T, and they'll put the steam trap in like this, and a bypass around it like that. I should show you a picture of this. I have it somewhere. And then you'll go off to your process like this, so that the momentum of the water and the steam basically carries it down into that T, and it basically throws the water up against that system. I know that doesn't explain it very well. Can you kind of picture the momentum? If the steam is having to change direction, the water is going to keep on going. It throws it into the steam trap system. So, does that answer your question? Not really, eh?
No.
Let's talk about it later then. Okay. Okay, so we know we've got steam control here. That's got to get hooked up from something in the bottoms control, and we've also got to get the liquid out of the tower. So horizontal lines break vertical lines. And we've got our pump system here. I need a motor. I need a motor control center. I need a DCS start-stop. I need a local start-stop. Like that. I'm going to need I'm going to put my pipe expansion in first. That's a terrible pipe expansion. I almost drew it like an eccentric producer. Okay, there we go, that's better. Just I'm bending down, I can't draw it very well. And I didn't win the graphics award. Okay, so this is basically the standard layout for a pump that I gave you guys before yesterday. Check valve, I want a manual isolation valve, like that. If you're worried about there being solids flow in here, maybe even for startup or anything like that, then it's not a bad idea to put strainers in the pump sections. I know that I don't think that's shown on the slides that I gave you guys yesterday, but there's a couple of different strainers. I'll just write this down. If you Google Y strainer, you'll see what they kind of look like. Usually you show them kind of like this. And so just for fun, let's show that. Let's show a couple Y strainers in here. I'm probably going to need a low point drain. And if it's a flanged valve, I'm going to put a blind flange on it, so that's why I put the line underneath the valve. I definitely want to put a pressure indicator on it. I forget whether it would be better to put the pressure indicator downstream of the Y strainer. I'm not sure whether that's common practice or not, but that would be the best way to do it. See, I'm really crowding myself in here, eh? So that's why you want to do a rough draft of these first. Okay, and I put my manual isolation valves in here as well. And now I just need to kind of hook them up here. And luckily, I've got enough space in here. Don't think I've forgotten anything. I should look at my slides from yesterday just to make sure I haven't forgotten anything. And so now we can take material out of the plant, and we've got this. That's going to be the cooling water side. So let's. Okay, so I have a hot fluid that I need to cool, and you can do this. You can think of this in two ways. You can either bring the hot fluid in and force it down through the heat exchanger or across the heat exchanger, or you can bring it in the bottom. And if you bring it in the bottom, then that makes sure that if the heat exchanger has got gas in it at any point in time, that the gas is removed out of the heat exchanger. So I'm going to bring it in the bottom so that I do indeed get rid of any gases that might be there. And that is the end of that bottoms flow, and that's going to our waste treatment plant, right? It's not quite done, but. And now let's talk about the controls here. We've got a couple of things that we're actually going to control. Since we're going to use a kettle reboiler, we'll probably have to put the level control in the kettle reboiler rather than on the tower. And we might as well pick up the temperature in the kettle reboiler as well. So I've got my weir in there. I need to make sure I got lots of space here. I'm going to put a sight glass in, and that might be a magnetic sight glass so that I don't have to worry about breakage. And then I'm going to put a level indicating transmitter in, like that. I need a tap, a flange, like that. Okay, I've got my level indicating transmitter in, and I've got a sight glass so I can check that stuff. I need some way to monitor the composition of the bottom of the tower. I'm going to do that by measuring temperature. It should mostly be water. So let's put a TE in, and I will put it here. I don't need a valve for a TE, and that's going to get wired into a TIC, and the LIT is going to get wired into an LIC. So let's draw those up here, like that. It's a DCS controller. There's an old style of P&IDs. There was two competing styles of P&IDs a long time ago. It's an interesting story. And I think DuPont had the one style of P&IDs, and I forget what the other company was. And DuPont's style of P&IDs was to draw the field instrumentation like this, and then draw all the control wires up to the top of the P&ID, and then all the indicators and controllers and stuff like that would be on the top of the P&IDs like that. And it made sense because that's kind of how the way the instrumentation was actually run in the field. It was all pneumatic instrumentation. It was really kind of neat because you have all the instrumentation up there, and then all the kind of the process equipment and stuff down at the bottom. And unfortunately, well, not unfortunately, but the ISA came along and they said we want to do it more with this style where we show the controllers closer to the equipment. So the history was that DuPont lost that discussion, and now the convention is to do it this way. But it's neat to see those old P&IDs. Okay, so we've got our level indicating controller and our temperature indicating controller here. It might be smart for us to put some alarms in here. So let's put a level alarm high and a low, and a temperature alarm high and a low in there. We're gonna have to start thinking about interlocks at some point in time as well. Now we've got a decision to make here around what do we hook the level controller up to versus what do we hook the temperature controller up to. We've got steam control that we've got to control, and we've got a valve that we need to put in this line somewhere. So we don't want to put the control valve here for this because we'll just cause cavitation of the pumps. We could put it here because we'll be at high enough pressure that we should be all set, and we won't have any cavitation. But we could also put it downstream of the cooler as well, which should make it just even that much better. So that's what I'm going to do. I'm going to put the control valve for level right here. Now, you could argue that we want to do a cascade on that, so we might want to make that a flow control loop and then feed the material and feed the control signal into that cascade loop, but I don't think it's absolutely necessary. Okay, so now we got to figure out where does that get its signal and where does that get its signal, and we have a choice of two. So if you looked at the rules of thumb that we talked about yesterday, what we're looking for is to see whether the liquid flow rate off here is significantly more than 10 times greater than the vapor flow rate that's going up into the tower. And so I'm going to go into HYSYS and have a look at, at what I have there, see if I can figure it out. Okay, so my liquid flow rate out is about 5,000 pounds per hour. And my vapor boil up is about 20,000. So you compare those, and 5,000 versus 20,000, they're different, but we could probably get away with doing either control scheme. But for now, I think what we should do is let's put the level control on the higher flow rate, which is the boil up. So let's do it. What I got to do is get a signal from there to there. That's two controllers talking, so I need a software signal. And actually, I'm going left to right, so I can either wind it around here, or I can bring it off the bottom. Let's bring it off the bottom, maybe. That might make it just a little bit easier to read. If you want to make your controls really easy to read, try and make the flow of information go from left to right or top to bottom. So if you've got a controller like this, show the outputs from the controller going in those directions. It just makes it a little bit easier for somebody to understand. In this case, it may not, but we'll try it. Like that. And if you want to, you can write the word SP, write the letters SP to indicate that that's a set point going into the flow controller, but you guys know that that's what's intended anyway. Okay, so that means that we're left with the temperature indicating controller that's got to go over to that valve, and so we just send a hard wire over there. And I know I've got to get all these pump controls in here, so I'm just trying to be as careful with space as I can be. And it would be nice if I could get straight lines here. If I have to move it around later, I can. Okay, I haven't decided what my failure position is on that valve yet. So, do I want to basically dump the contents down into the waste treatment facility and possibly the pressure, because it could be a problem. Actually, what could be more of a problem is I could end up emptying the liquid level and sending two phases into the pumps. I don't want to do that. Let's make it a fail-close valve. Done. And that's not an LV, that's a TV now. And that means that this is an FV. There we go. Okay, I'm gonna have to speed up a little bit maybe. That's the bottom of the tower. Now we gotta do the top of the tower. I need the same controls around the pump. So let's rip that off real quick. Check valve, isolation valve. Okay, pumps. Hopefully I didn't miss anything. I'm gonna need some level here. Like that. I'm gonna put a sight glass in again. I'm gonna put a level indicating transmitter in. I know I'm going to want a level indicating controller, like that. I'm going to need cooling water coming in here, so I'm going to bring the cooling water in from the bottom so it vents out the top. And I'm going to cheat right now, and I'm just going to put cooling water supply here. And I need an isolation valve. Should I cascade it? No, I'm not going to bother cascading it for now. So I'm just going to put a cooling water valve in and in. I'm probably going to want to put some PIs and some TIs in here. Okay, so this is going to be the cooling water return. Like that. It's good to have some isolation valves in case you want to do some maintenance on the heat exchanger. Okay, that's good. Now, I've got to get liquids coming off the sheet, and I've kind of blocked myself in with these pressure indicators because I should have thought about that. And I've got to get the reflux going up the top of the tower, so let's put the reflux in right now, like that. Wait a minute, I need some more space here. Okay, so let's put the reflux flow control in, and that one I am going to put on a cascade loop. Like that. I need an FIT. Like that. Like that. So I've got a flow control, I've got a level control here, I've got a valve here. What do I need to control? I need to control composition and pressure up here. So let's pick off our pressure here with a PID, like that. We'll put an isolation valve on there in case I want to do maintenance on it. And again, what you want to do now is look at the top of the tower and just get a sense of what the relative flow rates are in the top of the tower. So in terms of product versus condenser flow, flow going into the condenser. So I have 17,000 pounds an hour going off as overhead product. And coming in, I have about 36,000. So my flow rate coming in here is about 36,000. My flow rate going off the sheet is about 17,000, which means the reflux flow must be around 17,000, assuming that the vent rate isn't very high. So it's a wash as to which ones I connect those up, which one I hook up to the level indicating control. So I'm going to do it the old trusty way. I want to get my like that, and I'm going to draw smaller PIs here, just because that's a bad way to draw a P&ID. I wouldn't recommend it, but. And we need a valve here. Let's make that fail close because that's going off to a storage tank, and the last thing we want to do is send too much material into a storage tank in an uncontrolled fashion. So we're just going to bottle up the distillation column. And we've got fairly good residence time in here, so we don't need super amazing control, I think, on there. So I think we're okay to just send the level indicating controller straight into the valve. Actually, you know what? That's a slow variable. The level is going to be a slow variable. Let's cascade it after all. Then I've got a fast variable, which is the flow measurement. And I make it a software signal instead. Yeah, that's a better way to do it. Okay, so I've got that. Now my composition, therefore, composition and pressure. Okay, so the easiest way to do the pressure, as long as if your vapor flow rate was really a huge value, so that if you suddenly opened a valve up, you could depressurize the column, then you might want to put the pressure control on the vent rates. But that's not the case. that flow rate is really, really small. So the way to do this one is to put the pressure control on the cooling water, and I'm going to cascade that too. So there's my flow indicating controller, like that, and a flow indicating transmitter, like that, and I'm going to bring my pressure indicating controller here. Well, that's a bad circle. And this is going to be a software signal. Like that, set point. Okay, so that's my pressure control on the tower done. Now I need composition control, and really I'm only left with reflux, so that's kind of a no-brainer. So I'm going to use an XIC for my composition control, and it's going to be a software signal down into the reflux flow, and it's going to get a signal from a temperature element, and I can put the temperature element either in the exit line. You're looking to put a temperature element so it's facing into the flow rate. So if you've got an elbow like this in a piping system with flow doing this, your thermal well, which is basically what the temperature element sits in. So the thermal well is part of the piping system, and then the temperature element fits into the thermal well like that. And for you to have faster response, you want the thermal well to be facing into the fluid flow, so there's high velocity and lots of turbulence around it. It'll give you a faster response. So I'm going to put it in the piping. You could also put it in the tower itself. And I actually would like to know what the temperature is. So I'm going to put a temperature indicator in the DCS, and then I'm going to send that temperature indicator software signal down into my composition control. And also, I want to do pressure compensated temperature. So if the pressure isn't exactly where we want it to be, I can compensate for that in the software in the calculation of what the composition is. So I'm bringing temperature and pressure into my composition control. I'm calculating what the composition is, comparing it to a set point that the operators are determining, and sending the output of that controller into the flow controller on the reflux. Okay, so that's almost all of the controls, not quite. The next thing I've got to deal with is the vent rates. Now, because the vent rates are really, really low, and they're all non-condensables in them, so a way to deal with this is to put a little bit of a, you can either put a hat or a bump on the heat exchanger itself, or just, you can expand the piping up a little bit. Just somewhere to capture those non-condensables. And as the non-condensables build up in here, there won't be any methanol that's condensing. So what'll happen is the radiant and convective heat losses from this will allow the gases to cool, and there's no condensing methanol in there, so it just keeps on cooling basically down to ambient temperature. And so we can detect whether we have non-condensables in there simply by putting a TE. Whoops. A TE in there. And put a valve in like that. Okay, so I'm going to get rid of that because that's not part of the process. It's not what you normally put a P&ID on. Put a TIC in there, and that could be just an on-off valve. You might only open that once in a blue moon, or we can make it continuous like that. So if the temperature starts to drop, it opens the vent, and away it goes. And then what happens is the methanol gets sucked up into that area. It starts to vent a little bit of methanol, and the TE heats up, and then the control system sees that and closes the valve again. So, and that's going to go off to our waste heat boiler. Okay, we better put some isolation valves in there. So that's how I would do that one. And I might actually do the same thing for this one down here. And I think most of the non-condensables are going to get trapped in that one, but if I'm wrong, we'll get it in this one. Fail it closed maybe, fail it closed, and join the line so that we can minimize the amount of piping. No sense in running 2 lines to the waste heat boiler. Okay, so that's the non-condensables done. Oh, we're missing some cooling water here, sugar. Okay, so we want some cooling water supply here. I'm going to put my cooling water line here. I need a TE. Let's fail that open maybe. And TIC in the DCS. TE here, like that. Okay. Should be okay there. Did I miss anything anybody can see so far? Oh, down here, right? The side jar. Oh yeah, we need to get the side jar on too. Yep, good point. Okay, let's get this one on too. So this one's going to go fast, hopefully. Cooling water supply here, manual valve. Crank that open, and I need a temperature element here. Ah, darn. Like this. I need a TE here. Okay, that's really badly drawn, but I think you kind of get the idea doing cooling water loops. Side draw, okay. Which tray do we need to pull the side draw off on? 48? Okay. So, are you sure it's 48?
Yes.
Really? How much money would you bet on tray 48?
750,000.
How about if we hedge our bets and pull it off a couple of trays? Put some manual valves in so the operators can decide what tray they want to pull it off on. There's really not a good way to do the to tie a single loop control in there. So we'll just make that an FIT. To an FV. So it's basically manual control.
How do they know like which one?
Okay, so what I would do is I would put a sample valve in there. Now that is pretty hot, right? What temperature was it?
Hot.
Is it over 40 C?
No.
Yeah, it'd have to be. Okay, so we should probably have a sample cooler in there. So these are, you don't even need to specify these things. Often just write sample cooler. You should make sure we've got a cooling water supply and a cooling water return from them. And that'll keep the operators fairly safe. Valve. So that's how these P&IDs get complicated real fast when you start putting little pots and pans in like that. Okay, so that's our side draw. Is there another side draw? Just one, right? Okay. Now let's talk about some of the safety systems. We need a relief valve on here. Now we got a choice. Do we put the relief valve into the flare, or we put it out to atmosphere? It's a pretty tall tower. We could flare it. I'm going to say we're not going to flare it, just to be contrary. Okay. But I realize the potential of a methanol emission from that relief valve, and so I want to make it absolutely positively sure that there's not going to be, that relief valve is not going to lift. So that relief valve is going to have a set pressure. What's your design pressure for the column, you guys? 2.5 bar. Can't be 2 bar. Set at 2.5 bar gauge. Okay, that's pretty close to the operating pressure. I'd almost be tempted to push it higher than that, just to limit the to get it further away from the actual operating pressure. And then what I would do is I put a pressure switch in here, a pressure switch high in. And I got a choice whether I'm going to put a valve on that pressure switch high or not. I'm going to leave it off for now. That's going to make it almost impossible to do maintenance on, but it's going to be not more reliable, but it's going to be, you can't defeat the pressure switches easily. So not unless you enter. Okay, so my pressure switch is on there. What are the ways in which I could possibly get an overpressure in this system? Well, one of them is that the reboiler steam control valve may have stuck open, and the reboiler is putting so much energy into this that it's boiling all the liquid up, and it's generating too much pressure in the tower, and it's not being condensed by that system, or the cooling water system for some reason has failed. So what I want to do is I want to shut the steam control valve off. And I could do it by sending a signal into the flow controller with software. I could interrupt the signal going into the flow valve, or I could put another valve in, which is what I'm going to do. So I'm going to put an on-off valve. That's an HV. I'm going to fail it closed, and I'm going to send that. I'm going to send it a signal from an interlock, and it's going to be a hardwired interlock. Like that. Now, right now it's blind, and I can't tell that pressure switch has tripped the reboiler. So I'm going to put a pressure alarm high in the DCS just so that I know that something has gone. So I know what's gone wrong. So that's fixed a problem with the reboiler gone crazy. The other problem is potentially this system has failed, stuck open, failed, whatever. And so I'm going to put another valve in there to be on the safe side. So now what I've done is I've isolated most of the sources of energy that can put material into the tower. So I've reduced the probability of that relief valve. Did I miss anything? Just check my little rough notes that I had this morning. I think that's pretty much it. Oh, I know. No, there's a bunch of, you want to put a bunch of little temperature indicators and pressure indicators. So you want to, you know, when the heat exchanger is fouling, the pressure drop through the heat exchanger is probably going to climb. So just putting some little pressure indicator, temperature indicators in, and actually these can now be bought together. So they're a TI, PI combined unit because they're so common. So you can put a couple of those in. The other thing that's nice to have is you might want to measure the differential pressure across the tower. So you can do the whole tower, or you can do it in sections. Usually it's often done in sections, so above the feed and below the feed. So I want a pressure differential indicating transmitter. I need a valve, flange, and a valve like that, and I want to pull that into the DCS, pressure differential indication, like that. That's handy. We probably want to do the same thing down here. We could probably tie it into that one or put a separate one in. Depends on how we've done the feed stage, I guess. I'm not exactly sure how we want to do that. Transmitter. Like that. Okay, that's good. We're missing a couple of interlocks maybe down here in terms of the level. So if the level transmitter has failed, we might be smart to have a level switch down in here, probably off a separate tap. So let's put that in, and I really have no space down here at all. So I haven't planned ahead very well. That's a problem with trying to show stuff on kettle reboilers. It's easier when you do it on the tower, but okay, so let's just kind of draw this. Actually, you know what we can do? We can draw it sort of in the middle of the vessel here. So I've done this before. So you draw a little circle there, and then have a level switch low, like that. And that can have a level alarm low in the DCS, and then you may want to trip your pumps. So you can either send a hardware signal or a software signal into your pump control. I'm going to do it in software. And you'd be smart to do the same thing here as well. Like that. And we are basically done. I'll probably think of some stuff over the next couple of days, and I'll add it in red. So it's unlikely that you would get through something like this in a first go and not think of stuff you want to add later on. Any questions? Did it help? Yeah? Kind of get a sense of the way you think it through? So a lot of it, like the pumps and stuff like that, is just sort of copy. Well, unless you guys have any questions, I guess I'm done. Thanks for coming, guys.